Okay, I want to continue on where we were last time with our looking at TCP/IP. Just at the very end, the last slide, we um, ran out of time for IPv6. I'm not sure what happened to IP version 5, but IP version 6 is the next kind of IP from IP version 4. The thing about IP version 6 is it's got 128 bits worth of addresses, and so it makes it, it says feasible to be very wasteful. 128 bits is, I've seen it say that there's, you could have an IP address for every grain of sand kind of thing. So there's a lot of addresses. Mostly IP version 4, which we're used to, which is, has the 4 dotted decimal spaces like 10.0.0.55 or what have you. Most of that is still in local networks. Most routers understand IPv6. There are, just like there are IPv4 routers out in the world, there's IPv6 routers, and you can subscribe to get an account on one of those routers and get your personal IPv6 number, and you can have things redirected to an individual device in your network and things, for instance. There's lots of new features, and again, some backbone stuff is used. It's not used a ton yet, but it's out there. And again, when you do, for instance, check your internet configuration, you will see an IP version 4 address, and you'll also see an IPv6. And it's, 8 blocks of 4 hex numbers is the way it's displayed, with colons usually in between. If I spot it in one of these things, I'll point it out. So when we looked at the OSI model and then the IP, TCP/IP layer, this is just kind of showing when you send from one device to another device, especially if it's not in your network, it could jump through a number of different nodes, and this is just another representation of that. So if I am an application, let's say this device, I am wanting to send something. For instance, I have a Google browser and I want to go to a web server. Then as far as my browser is concerned, it's talking to this web service over on the other side. And so there's peer-to-peer protocol. So there's a protocol from here, from the web browser to the web server, and it's just sending data as far as the applications are concerned back and forth to each other. But how it actually does that is it bundles up, and we looked at the stack, it bundles up the application and it goes down through the layers. Again, we had in IP, it's a 4 layer as opposed to a 7 layer, but we had the TCP information get bundled up in the IP information, get bundled up in the MAC layer, and it gets sent out. So it goes down through the protocol stack, and then it's going at this network layer. It's saying, was it in this network or another network? It goes, it's in another network, so it puts in the MAC address at the data link layer, so it sends it to the router, and it puts the 1s and 0s on the line. The 1s and 0s are received at the router. It goes up to the data link layer and it says, is this my MAC address? And it says yes, because it was the MAC address of the router. And then it goes up to the network layer and it says, what IP are you looking for? And let's say it's somewhere in Australia, and I go, well, I don't know that, but I'll ask other routers and I'll send it to the router going towards Australia. So then it says, okay, what's the IP of the router that's towards Australia? And then it bundles that up and it says, okay, well, then depending on whether I send it out with a ATM or through satellite or what other kind of communications, it has the MAC address of that, and this MAC address changes and it goes to this other router that it said was it forwarding off, and it says, hey, is that the MAC address of this router I sent it off to? Yes, it is. Then it goes back up to the IP and it says, oh, that's an IP for somewhere in Australia. I don't have that, but I'm going to send it over to this router I know that's in Australia. And then it goes and it says, okay, well, where's that router? And so it bundles up the MAC address of that router, and then it goes out through maybe a satellite link over there. Then it receives it on the satellite link, it goes up and it says, is this for me? Is that my MAC address? And it goes, yeah, that's my MAC address. And then it goes up to the network interface and says, is that the IP address? Do I know where the destination is? Maybe it's the destination that's somewhere in your network, in which case we can go down through the protocol stack again. And then when it comes up and it goes to the router in the network, and then it'll go and do an ARP advertisement, which is a broadcast, and says, hey, who's got 142.31.204.17 or something like that. And that's a MAC broadcast that goes out to everybody. And so all the different network cards listen to it. And then somebody goes, hey, that's my address. Here's my MAC address. And then it goes and sends it over there. And then it goes up the protocol stack. And then the web server says, oh, decodes that, and as far as it's concerned, it just was peer-to-peer talking from the Chrome interface to the web server interface. It's looking at that, but it went down through the protocol stacks and up through the protocol stacks and down through the protocol stacks, only a little bit going through the hops, just enough to find out the IP address of the next hop along the way. And we can use different utilities like traceroute to be able to look at the hops along the way. So if I went, and it's spelled slightly different on Linux and Windows, but it's trace RT or trace RTE in just a Windows command prompt, and you go trace route, for instance, www.camosun.bc.ca or something, or google.com or wherever, and it will show you the hops along the way. It shows you the replies of all the different routers along the way, and it's doing this thing. Okay, it's going through all of these different hops.
How much is that scale? Is it thousands of routers?
No, because don't forget, every time it goes through a router, it takes off from your time to live. So generally, you'll see things if it's really close by, 3 or 4 hops. You might see something in 17 to 20 hops kind of thing, and it goes and it tells you, it shows you the milliseconds coming by. Now, some routers also go, I don't want to talk to you, so it just gives you no information from that. As it passes on, it doesn't tell you some of the information. So you'll see some of the trace routing going through there. I wonder if let's see if I can, I'm not sure what my Wi-Fi is like. We'll just see. Um, um, I don't know if I even have it installed here. Oops, it's not even responding to anything I'm doing. Let's go to, I don't know if the college is blocking anything or if it's letting me out. So Amazon.ca customer on a network called fastly.net at 162.219.266.231, and it says it's more than 30 hops, so it's more than 30 routers away from wherever we had, and it's saying, hey, it took me to get out of the network. We have 350 milliseconds before it was responding, and then it's saying number 4 here, it's saying, hey, it's not giving me any information back, so it requested information. You see all the IPs of all the different networks on there. And then this one is a gv.shawcable.net we're on. So different routers. We're still in Shaw Cable. Passing around a different one. Now we're on fastly.com. The Amazon.ca is on fastly.net. So at least we're over that. And so it says, okay, it took us 9 routers to get through. So it gives you some kind of, so it went through here, through here, through here. It went through 9 routers to get to Amazon. Okay. So We'll look at in this lab that you were doing, well, last week's lab and more this week's lab. Last week's lab, we looked at looking at TCP. And the reason I was looking at this, so there's time this week if you didn't get it done during, because we had a test and things as well last time. So you have this week to work on it as well. I do have another lab for you this week, which is very similar to last week, and we'll just talk about it here. But it says follow week 9 with the ESP 8266 AT documentation to set up the required hardware and software. Essentially, you take your TFT touch and bring in the libraries to be able to talk to your ESP 8266 with the AT firmware. And so in the ESP datalogger.c file, I want you to copy, I would copy ESP send and make an ESP send TCP in order to send TCP addresses. Now, and then I wanted to send temperature at a 5-second rate. And so here, if we look at our packet sender, we see TCP. I sent it to 8080, whatever one you have there. Again, your AT firmware doesn't want to send to a port number above 4 digits. So that's why I said just go pick a 4-digit number. You might have to set it. In Windows, when I go and set it, it often is at least a 5-digit number there. And so your AT command won't like to send to something like that. And then what I wanted you to do was play with the logic analyzer that you have and be able to have a look at the data. And sending serial data is awesome. It gives us a nice window into looking at what kind of data is there, and if you're sending what you think you're sending, and if the AT firmware is responding back. And without that, it's really hard to see what's going on or see where things aren't working. And so we can go and have a look at that. The protocol decoders, which are here, and we picked a UART. There's a ton of other decoders. When next term you'll use the logic analyzer and look at the infrared decoding that's on in your Kuman kit, you have a little remote, a little IR remote and a little IR detector, and we're going to interface Linux to be able to go and respond to that and be able to control some stuff with it. So in order to see what you're getting out, we would set up NEC-IR protocol, which is what your little remote does, and have a look at the data that's being blasted on the line. So the logic analyzer is a nice thing to have. And there's lots of decoders available under there. And so we're just looking at a simple UART. And you'll see it say UART or USART. Originally, they were all UARTs, which is Universal Asynchronous Receiver Transmitter. They now you'll see them say USART because in the same firmware on the module, they also put the ability to do the synchronous stuff, I2C and SPI. So it's all in one module. So you can see it, we're using the UART part of it, but you'll see it replied to in both those cases. So in this case, I wanted to see that you could get the logic analyzer going and see some data, and that you could send TCP with your lab. So in the next lab, this week's lab, so if you have that going, it's a matter of copy and pasting your send TCP to a send UDP. And the reason I wanted to do the UDP is it's a little easier to look at the data because we don't have the three-way handshake of the TCP and trying to decode what's going on. We're just sending a packet and forgetting it, kind of thing. So it's easy for me to just grab it in a program called Wireshark. So last week's lab was about looking at the data on the serial. Well, now that we've seen the data on the serial, it's now let's look at the data on the wire or in wireless. Let's look at the individual packets. And there's another package called Wireshark, which will let us look at that. And so I want to see the sent packet from packet sender, and then I want to see the SIP start and pulse view showing me that you're sending the UDP. And then I want you to upload a screenshot captured with Wireshark. And so there is our packet sender, and there is, again, let me see if I've got this. if you see the data. And it's if you haven't looked at it yet, it's really kind of neat in that you can zoom right in. And one of the nice things about you can either look at the individual bits, and so you can zoom right in on this data and actually have a look at the start bit and then the zeros and ones, least significant bit first. But because we have the protocol decoders, it looks at these blasts of data and says, oh, well, you can have this show you ASCII, and then it'll say, oh, well, that's an A and a T and a plus and a C and an I. And so you can decode that nicely. And then we get a response back saying that it's connected and things. So you get to see all of that kind of stuff. And then on the UDP, I want you to fire up Wireshark. And Wireshark, again, like the logic analyzer did to show us the serial data, then Wireshark is going to show us either the packets going over your network. And so there's lots of packets going over the network, especially in the college here. And I can search, for instance, for UDP. You basically you click on the little shark fin and you grab data. When it first starts up, there's ability to look at some Bluetooth and some USB and some other things. We just want to look at your wired connection. If we're going to, for instance, be wireless from your computers in the lab to the bakery router, you just want to look at the wireless interface. I want to get rid of most of the other stuff. There's a lot of packets going back and forth. And then you can search for different protocols. I can search, for instance, for UDP. So anything that's running at that kind of layer in the TCP IP, you'll show up. And for instance, here, you can, I have my IP going to the IP of the packet sender. And so I have this whole frame. And so I've found that going, oh, that was me. That was my IP address. This is going to this is the IP address of my firmware on the Node MCU. This is the address of the packet sender. And then I looked at UDP and it says it captured a frame or 56 bytes. And there it shows the 56 bytes. And there's my name, colon, 18.8 degrees. So it's showing that you're getting it there. And of course, when I go to up to here, it should be showing me, well, when I grabbed that one, it was at 19 degrees. So it should be showing me the same and sending with UDP. So I want to just kind of look a little bit at, go up to frame. And I want to go back up in this document to, where's my IP? There's my IP. Okay, so if I have IP, it says here is an IP datagram and there is a header. And so we have a header and all of these are 32 bits and we have 1, 2, 3, 4, 5 32-bit words that include your version, there's time to live, there's source destination, and then there's some optional things. So there's a bunch of options we can do which are not normally you're going to find done. And if it was less than 32 bits, then it would pad it out to 32 bits. And then here's your data. And what's in your data is, are you sending TCP? Are you sending UDP? What are you sending? Because that's the data that was encapsulated by the IP. So I just want to reference this when we go over and look at Wireshark. Now, when we go over, for instance, to Wireshark, you can save your capture. And so I just saved the capture, double clicked it, opened Wireshark and says, here it is, because I knew when I'm in this room, I wouldn't capture anything. And so I did this beforehand. And so here is 10.0.0.221 over to 10.0.0.175. And so I see a whole frame. So if I just click on that, it's highlighting, here's a whole frame, here's 56 bytes that were on the wire, and we can see there is the MEL 18.8 degrees. And so that is a frame going out. And then so I have a MAC address which is going out, and it's going to have a source and a destination. And in this frame, what I'm running is Ethernet. And so if I click on Ethernet, then let me just expand that kind of thing. And it tries to show me the various parts if I highlight various sections. So one of the things here, if I click just on destination, the very first thing coming out at the frame layer, going out to everybody in this network, I can't get beyond the router, but just in this network, the very first thing is the destination address. And it kind of makes sense in that if I'm sending stuff out, every network card listens to it because it could be for you. And so I either have all Fs, which is a broadcast, which goes out to everybody and everybody takes it in, or it's the individual MAC address. And so if I'm sending out to 9CB6095F849, well, that is actually wherever my packet sender was, the computer that the packet sender was on, that it's going to send that information out to. And so all the network cards listen to it and they see the first 6 bytes and they go, it's most of the network cards go, it's not for me, done. Only the one that says that's for me takes in the rest of it and goes on. Everybody else just had to listen to 6 bytes and then say that's not for me and done. So I either see all Fs or I see its address to me and the network card can then bring it up the chain, bring it up the stack, okay? And so the next thing, if it is for me, then that network card starts listening and going, hey, who's it from? And it's from F4CF A2EFBC92. That's the source. And you'll notice here, Wireshark knows, so the destination, for instance, was to a machine that had a RivetNet network card. It took the 6 bytes that we said the MAC address was, and we said the first 3 bytes was the organization unit identifier, the name of the company that made it, and the next 3 bytes are the individual network card address. Well, Wireshark knows who all the manufacturers are, and so they try to help you out, and they said, hey, this here is RivNet, and then it's 95F849 is what's going on there. And then, so who's the source? So if I click on source, then it goes, hey, Espressive. And so that's who makes the chip on your network card. The Node MCU has the Espressive ESP8266. So it knows that and it says, okay, it's an Espressive. And then it has the individual one. So you'll all have source Espressive something. Okay, so it's decoded that just to make it a little easier for you to go, I don't know who that is or anything. But it's saying, hey, this is the one. So I just click on it. And then IPv4, the code for IPv4, because you could have sent something else on there. There's used to be Novell used to have IPX. It was at the same layer, so you could have IPX instead of IP. That all disappeared. There used to be Novell certified engineers, and everybody would write exams and be Novell trained and all of that. And IP just slowly won over basically everything. And then the other thing that we have here is a little trailer, and that is your packet didn't quite make up enough for the minimum number of bytes to send, so it padded it with zeros. And so that's, so when I go and click here, there is the frame, the Ethernet addressing for source and destination. And then I'm going to say, okay, well, what's traveling on that Ethernet frame? And so what we have, so this changes the Ethernet layer, that MAC layer, we said through the different routers. So it's going from one area, it goes up the protocol stack till we get there. It says, we'll look and see what IP address it needs to go to, and then it goes back down, and it goes up all the way to the IP layer kind of thing all the way along. And then so here, I'm going to shrink that down and say, hey, well, where's the IP? And so there's the Internet Protocol version here. And if I highlight that, then it says things like IP version 4. So it says this is the 45 in this. So it's in 1 byte, it is the 4 and the 5. So I want to go back to, if I can find out where I put it here. So I want to go back to the IP datagram. So there's 4 bits for version, okay? And so 4 stands for IP version 4 in the IP datagram, and then a length is 5. And what it's standing for is 5 32-bit words, 1, 2, 3, 4, 5. So it doesn't have any options or padding in this case, and it will have the data after that. But oftentimes it doesn't have this. But you have this 1, 2, 3, 4. There's 5 32-bit words is what's going to make up my IP header. And so when you look at that, that's going to be the 5. And it says 20 bytes because it's 5 32-bit words is 20 bytes of information. And then, so we go down through this and we say, okay, we have different parts in it. Time to live is one. There it's FF. And again, as we go through routers to routers to routers, it keeps taking off that. And when it gets below a certain number or 0, then it doesn't forward it anymore. It throws it out. It stops these packets from going around forever. And I say when it gets to 0 or some other thing, your router can decide if you're below 20, the number of time to live is below 20, don't forward it. Like you can configure those kind of things as well. Maybe you're getting too much traffic from far away hops or something like that. Okay, and so let me go to, so that was that whole part there. And then there was data, it said at the end of that header, and the data is here. And if I go and look, where's my thing? And so we had the header, and we have the source and the destination address. So let me go back to that. Source and destination address. And so, not in this one, and I should have my source address is saying, hey, there is 10.0.0.21. There's 10.0.175. So that's buried in the IP header. And then so at the IP layer, this packet moved from any one node to any other node in the world at that layer. And then we said, okay, well, UDP and TCP go to one other layer. We need to know what port you're sitting at, what address that is. And so if I look at the user datagram, it says, okay, my source port here, here is the, let me click there. Here is the header for the UDP. And so that looks kind of small. Let me just go over to here, and we'll go down a few to UDP. So this one had all sorts of things: version of IP, length, different fragment if there was multiple packets, the time to live, the protocol IP. There was a header checks on the source and destination. We have all of that kind of information. And if we go down to UDP, it's quite small because I'm already I had enough information to get to the destination machine. And so now all I have is the source port and the destination port, and then the length. And so the length of the UDP header plus the data is what there. There's also a checksum to say, hey, is the data right? And then the actual data itself. So that's what's in the UDP. And so when I go over here, I look at UDP, it's here. And it says, okay, the source port is all the ports below 1024 are reserved for things like HTTP, ICMP, FTP, all of those common services. And so anything that you use would be above 1024. And so it grabbed a port number, a random port number above 1024. And then where's it going? It's going to destination 5555 because I had to tell it that's where I want it to go because packet sender is sitting with the UDP at 5555. And so if I have, where it's in here, packet sender is sitting there with UDP at 5555. Okay, so randomly it made up the ESP8266 firmware made up a port above 1024. It's going to 5555. It says the length is 19. And so, and then it says the UDP payload is going to be 11 bytes. And so if I just highlight, there's my different 11 bytes of information. So we've got our source, our destination, the length, all part of the header, and then I have my actual payload of 11 bytes. And what is that made up of? that it nicely goes and tries to decode some of it over here for me. So there's the ASCII, there's MEL colon space 18.8 degrees. And because there was also in order, so that's the whole packet that I'm sending, and to make sure that the frame had the minimum of 56 bytes, it padded it out with 3 zeros. But the actual payload on the user datagram knows that it is stopping with the 11 bytes, knows that it's stopping there, and the rest of it is just padding. Okay. So if I go and let's just see if we can do this. I will have to see. Not open. Okay. Well, I don't want to open. I just want to run a new one. Okay, so when you open up Wireshark, this is kind of what you see, and I have a capture area here, and it says use a filter, all interfaces showing. I don't have kind of any filter. Let's have a look. All interfaces shown. Should just start. Come on, capture. Manage interfaces. Of course, it won't show me any, and that's, just taking a long time here. So if I go over and look, there's a whole bunch of different network connections. You can look at some Bluetooth data. You can look at your wired connections, for instance. There's Wi-Fi, and I was just looking at Wi-Fi is all I wanted to look at. Let me just see here. What's this? Promiscuous is by default on, and if your hardware supports it, Promiscuous says, even if it's not for me, even if it's a malformed packet, I want to look at the information on the wire. If you can't get your network card into a promiscuous mode, it'll look at what's good and destined for you. Promiscuous mode lets you say, just show me what's there, and it's used if we're going and debugging. And then if we go start, then we'll start to see a bunch of packets on the line of all sorts of different information. We can apply different filters. For instance, you can say that you want UDP, and then it should show me, and then I can go, let's go stop. And then I can have a look at all sorts of different things that are on the wire and go through and say, okay, which one, look at, you can arrange stuff by source. So you can go search for whatever your IP is, or you can look at stuff at destination and say, okay, a bunch of different modules are sending it to one packet sender server. So you could just go looking at that. And again, you can look at TCP or UDP, TCP. Because of our handshake, it's a little bit trickier just looking at something because there's back and forth communications. So this is sending an acknowledge to a previous TCP packet, for instance. So it's a matter of you turning this on for Wi-Fi if you're connected to Wi-Fi using the bakery router, or connecting to local, for instance, in 204. Most of the machines in the center ones, for instance, or you'll see them just behind the machines. There's what you're connected to right now, and there's what's known as the L port. So if you have a network connection, it might say 20, and then it could say L20 on the other side, for instance. And the L's are connected to the rack by the door in 204. And so it's all wired up on there. But if you want to, instead of be connected to the college's main network, you want to be connected to the router that's in 204, you can plug it into the L port. Okay. And that will be you hardwired connected over to that bakery router. then your ESP8266 can be connected wirelessly. If you do that, just when you need to check out your IP and see that you are connected to the 10 network, or instead of the college's network, and that you're on the same network as your wireless, so you're on the bakery router. If you do that at the end of class, you need to make sure you go back to the other connection. The machines we just got just 3 weeks before the term started, they all have wireless. And so even though you're connected wired, you can attach the wireless to the bakery router, and it'll let you keep both connections. And then you can just search on the wireless connection over here, instead of everything just connect Wireshark to the wireless, and you'll just see that connection that's going over to the bakery 204 router. So it's nice in that you don't even have to change the wiring and all of that kind of thing. So you can do that. So I'm hoping it's not a big lab. The whole idea here is, over the last couple of weeks, it's like, look at the logic analyzer. It's a handy tool. Look at the data. If your AT firmware isn't working, it's really handy to go and look and see what that node MCU is spitting back at you, whether it acknowledges things. I've checked on the wire and seen, oh, it's error, or it's busy because I'm sending data too fast to it. Maybe I better hold up. The while wait for OK should take. Sometimes you haven't flushed a buffer, or it needs a little bit more time, and you might need to put a little bit of a break in between it. But it's really hard to tell what you're doing unless you're able to look at that communications back and forth. And that's where that logic analyzer is really nice for that. Then on the UDP lab, it's about looking and saying, for the same kind of idea, we looked at the communications between your ARM board and the ESP8266 to make sure that was happening. Now that data is going out on the wire, looking at your UDP packet, for instance, do you actually see it? Is it actually transmitting? So if it's actually transmitting, then are you on the same network? That kind of thing. Like, why isn't your packet sender maybe getting data back? If it's sent out on the wire, it should be getting it back if they're on the same networks. But it's able to look at those kind of things. A number of years ago, before we had inexpensive little wireless connections and all that, I would go trolling all the used computer shops and things for Realtek network cards, and using the PIC microcontrollers. You guys would get an ISA socket and put it on a board and wire up a network card to your PIC. And then we didn't have a whole protocol stack. You actually had to look at the UDP packet and build the 60 bytes in order to make the whole thing send. And so you would say, okay, here's the source, here's the destination, build a 60 byte array and just send it on the network card, and then your data would show up and things. But we didn't have the inexpensive. Now you're looking at an ESP8266, $3 or $4, from AliExpress or something like that, and you can send stuff on the wire wirelessly. So it's good for being able to make data loggers and all of that kind of stuff happen. Going to leave it there today. We're going to talk more about Internet of Things and some of the different places we can set up to. I hope this lab wasn't meant to be too onerous. The UDP to TCP is a very short changeover, and it's more about playing and seeing that you can see data on the line with Wireshark. Thank you.